Oh, you're. No? Okay. But your phone also is not on? I hear some echoes. You also turn off the sound. Yeah. Yeah, maybe just a second. Yeah. Okay.
The sound is working.
Yeah, that's good. Okay, let's start. Then slowly. Hi everyone, thanks for joining. So it's a great pleasure to have Ivan Laptev. So Ivan is now a professor in MBZUAI University of AI in Abu Dhabi, and also he's on leave from India. Before that, he was a director in below team in India for something like 20 years. No, you've been in India for 20 years. For 18 years. 18 years. And he did his PhD in KTH in Stockholm. And actually, part of his master, he was here for master thesis in TUM. So after 20 something years, he's coming back. So Ivan did a lot of cool works on video understanding, object recognition, and nowadays we are a bit collaborating also for robotics. And we are looking forward to hear from you.
Okay. So thanks, Majid. Hope people can hear me on Zoom. And yeah, thanks for inviting to this talk. So I think for me, it is a bit special. So as Majid said, okay, I can use the okay now. Yeah. So actually, this is the building where we are, and that's where my career as a vision researcher started, because my first paper was produced in this building. So it was ECCV in 98. I think it was the photogrammetry department, which may not exist anymore because maybe a computer, everything was solved for them. But yeah, I'm not sure. But it was here, so I was happy to spend my master project in TUM in this building, and then I was actually starting PhD also in somewhere in Ostbahnhof, and then I eventually moved back to Sweden, where I did finish my PhD. All right, so let's move on for today's talk. So I'll start with. So it's going to be a bit about video and a bit of robotics. Not much robotics. How many of you doing robotics here? Because more than half probably. Yeah. So I'm not a roboticist at all. So I'm pretending to be a roboticist with the help of Majid. So I did for my since PhD and later. So I did work on video. Okay. So what is video? This is one type of video called time lapse. Right, so I like this video because it's kids doing a really good job. These are not my kids. So my kids usually do it. If you play the video reverse, that's usually what my kids do. And yeah, so you want to have these kids who are so good in cleaning house. I gave up. So actually, what my motivation partly to the robotics is also is to have a robot which will do the job. And so now, okay, this is a visual problem because we need to. It's not a factory where the robot does the same thing 24 hours 7, right? So all homes are different, right? Every time we do the math, it's different. So it's a perception problem. Obviously, we need to connect perception and robotics. And as you may know, so computer vision has progressed hugely in the last. Say 12 years at least, so it was a huge boom. So say object detection, action recognition, whatever it is, putting labels on something. So human pose estimation, 2D or 3D, these are quite now. It was a huge challenge 10 years ago. Now it's in the industry, it's quite easy, at least to get some reasonable numbers, and it's in production, so things are working. And most recently, of course, we have the also GPT models, large language models, also or vision language models, which understand images and video in which you can interact. You can ask questions. You can just say, describe this image, and it does. For this image, it does really good job. So it does says the boys in the red shirt, like doing vacuum cleaning, and this is actually amazing. This is something what, like 5-10 years ago, people could not even think that we will be here. Okay, now the point is, so okay, all these great tools, how do they bring me? How much do they help me with my task of creating a robot which cleans the rooms? So can actually all this great progress in computer vision and language, can it actually help to us now to make so intelligence robots to transfer all this success to robotics? Okay, so that's the question. I don't have a good answer. I just tried a few images on GPT recently, and surprisingly, some of them really worked. Okay, so my talk was motivating. Okay, vision is kind of getting solved, but in what sense? Internet images, because you have lots of data of paired data of images and language. Okay, you learn models, and this that's kind of internet data is lots of data, so you can solve it. Now, what these large models don't have, they don't have access to physics, they don't have access to actions, like material properties. There is no data for this. They could be potentially inferred from images, but this is indirectly. So embodied understanding of scenes should be hard, and it is still hard, although in some cases it does solve it. But this is one example where actually it doesn't work. So I'm just telling GPT-4o, so I'm a robot. I want tell me what should I do to put milk from a purple. I don't know why this. Anyway, so this purple container in the back, and there's a green bowl. Okay, so it's not trivial. So we need to decompose the scene first. You cannot just pour something into green bowl. There is lots of stuff. And okay, so it does produce the recipe how to do it, but it does not really. I mean, it's a general recipe. It's not connected to this image, really, because it just say, okay, clear the obstacles, like pick up the purple container. Yes, maybe that's easy, but then position the green ball, and that's already a problem. How to need to do something before that. So here it doesn't work great. So here's another example. So asking, where can you comfortably cycle with this bike? Okay. It tells us the places where we can cycle, but doesn't notice that there is something wrong with the bike. And okay, similar with this bag. So it's, if there's some problem with this bag, we cannot really carry it, right? And but still, so there are a few examples which really amazed me. And then I was trying to really tweak it. So where does it fail? So here's one example which I found interesting. That okay, this is a scene actually that's not from internet. It just took a picture of the scene. Okay, it described it as a pen, as a table. Okay, and now I'm asking what will happen if I put my hand up. What will happen if I put my hand up in this image? What's your guess? Okay, so that's what GPT thinks. If you move your hand up in this situation, then you're likely to lose its balance forward. So this is quite advanced. I mean, it does understand something about physics. I mean, explicit, well, we don't know explicit, implicit, but somehow it learns, it knows about the things. Okay, so the pen is standing because it's stuck in this hole. And so I'm asking GPT, are you surprised? So yes, it's this is interesting situation because it still thinks that the pen should fall, and it thinks that it's like balancing really. So why I'm saying this? So like 1 year ago, I thought that the language models, they like no chance they will help us on a low level. Okay, so we know that now that they can produce code, produce recipes. So it's not surprising that if I ask like, what should I do? Like, I'm a robot. What should I do to like to make a coffee to give me high level recipe? What to do? Which is okay. It has learned it, but on a low level, I thought it will never. So it seems that it does understand low level motions well, but we are not there yet. And how to get there is still unclear. So that's what we are trying to approach from different directions in my lab. And so we are basically trying to combine language, vision, robotics in some sensible way. And I think sensible way, which to me is interesting, is to answer these two types of questions. So given an image, because we want to be, like, it should be sensor-based. We don't want to assume much about the scene. So what actions are needed to bring the world from one state to another? So this is quite a general question. You are repairing, I mean, you are renovating your home, or you're cleaning your room, or you're making pizza. That's the question. The robot should know it's supposed to do that. And once you plan, okay, so maybe it comes up with a plan, then you also want to maybe verify, is my plan correct? So I want to ask the computer should be able to tell, like, if in this given scene, if I do action X, what is going to happen? So these two types of questions are, I think, very interesting and still largely unsolved in computer vision, and relates computer vision to robotics. So question is how to learn the answers, how to learn to answer such questions, right? So that's part of my motivation to the talk. And so we've been looking at this question. We are still far from solution, but at least one approach to address this is to look at specific type of data, which are instructional videos. We've been looking at this for some time. And so if you haven't seen, I'm sure you've seen what are instructional videos. These are something people put on the internet in huge amounts. So for lots of different tasks, like you probably seen these videos. So yeah, if you don't know what to do, especially mechanically something, so or on computers, so you go on the internet and check it. So why is it interesting for us? So for several reasons. So first, it's very diverse. That you have for the same task, you have different objects, scenes, right? So that's, I think in robotics, this is one problem, because you do experiments. You want to do, well, either simulation or real robots, so they are very limited to this. You have just one scene in the lab. Maybe you have 10 labs collaborating, but this is very. So here you have really lots of diverse scenes, which is good. Lots of different tasks, and also people. Not just that, people also narrate this video. So you don't hear it, but all these videos, they are narrated. Means we can transcribe the speech to text, and then we have also a description of what happens. So this description is not like one-to-one. Just people are talking. Okay, sometimes they talk about some unrelated things, but eventually sometimes they mention what they do, and that's kind of free annotation for us. Okay, does it make sense? So okay, these are a few papers we published on this, and today I'm going to talk about. I will start my talk by talking about these two papers, which was CPR 22 and CPR last week. So these papers are following the rationale that states and states changes are important. So because you renovate your apartment, you have before and after images. Okay, these are big state changes, but then like you have intermediate state changes. Right? So you put the wallpaper, whatever, right? And so we were interested in the question of identifying these key state changes and also actions which bridge one state to another. So I'll talk about these for first recognition and then also generation. We'll see in a minute what I mean. So what are the state changes? This is an example from our quite early work. So that you have cup empty, okay, you pour the coffee into the cup is full. This is an example of a state change. And of course, well, you can nowadays learn whatever in images or videos if you have annotation, but the type of number of actions, number of states is in general is very huge, so you don't want to do any annotation. So the goal of the work was to try to discover these states and actions automatically, and again with the motivation of doing eventually doing robotics, but we are not yet there to connect really this to robotics. But what we have this huge amount of data. So that's and you can even you don't even need to be Google or Facebook to collect. So we had a one and a half student project, which 3 years back, so collected 100 millions of these YouTube videos, and then so how basically that's here is the part. This is the raw data which we feed into neural network, and neural network is doesn't have any supervision, but so it tries to find, let's say, initial state. So we know that this is feeding apple, or we do something apple pie, and the feeding apple happens inside because the person said, "Now I'm feeding apple." Okay, so you have maybe 1 minute or half a minute of video, and we know that feeding apple happens there sometimes. So, and we don't have just one this video, hopefully we have hundreds of them. But it's noisy eventually, maybe it peels the apple, maybe the person does not peel the apple. And so now we want to, without any further supervision, we want to identify what is the state of unpeeled apple, what is the action of peeling apple, and what is the state of peeled apple. Okay, and so how this happens, so no supervision, but we need assumptions. And assumptions used here is that first appearance, so appearance of unpeeled apple that should be similar in all the videos. Appearance of peeled apple should be somehow similar in all the videos. So that's one. The second assumption important is the temporal order. So we assume that there is a strict order of state 1, action state 2. Okay, so that's the basic assumption. And then, so this is for, and then also we can assume something about negative data. So you see the green errors. So this is basically make assumption that these images should be similar, and the red errors they should be different. So I assume you are familiar a bit with vision, like CLIP. Do you know CLIP model? Right? So that's that's the contrastive learning. You learn text and image. Right? So you have paired data. You try to put images and corresponding text in the same place in the feature space. So similar here, we have paired. We kind of try to find paired data for unpeeled apples, actions, and that. Okay, so hopefully, if you have any questions, let me know. So it's a contrastive learning. I'm not even showing the loss or the network. It's well, it's contrastive learning with specific constraints which are created for this data. Okay? And what are they? But data is very noisy. So the challenges is that obviously we know that visual variability is huge. You can have this, I think, was action of blowing a balloon. So balloon can look very differently. So videos can be very long. So you can be minutes long, and you have to find the right. So we don't have any supervision. We need to find the right spot during training. So this happens automatically during training, and sometimes on the right you see the videos are not even not relevant. Okay, some of the videos are not relevant. Right, and then there's some still some annotation for testing, so to measure how well are we doing this on this task, how good we discover the states and actions. We actually do annotate some videos and measure performance. And so here are some results, qualitative results. So top we see the exchange the data set. That's what data sets. Very, very different types of tasks like paper folding or tortilla warping. So I think this video should also show a bit more. Okay, so these are just three random videos of paper folding. And during training, that's what the method identifies. So this is the state of paper unfolded. This is the action of folding. And maybe that was not just folding, maybe it was folding of airplane. Yeah, that was more precise. Right, and that, so it does find the final state of folded airplane. Same thing for the fish. All right, so maybe move on. So many examples. Okay, we have evaluation with a data set for this, so we can measure performance. In terms of action detection, detecting the action, detecting the states. All right, so that's how is it useful? We still don't know because the robots which can do the fish or peeling apples, well, we are not there yet. Unfortunately, otherwise, hopefully, somewhere at some point we will be there. So this data will be useful. We can just learn directly from human videos for complex tasks. So here, what you think is a bit of one small step still towards robotics is that we are not just identifying in the video the states and actions. Now we are actually using that data as a training data. We are now learning a model which generates the new states and new actions. And so what you see here, the first image is a real image. So that's what you would take in the kitchen, and then you would say to the robot, peel on chopping board ananas and pineapple in the blender, pineapple smoothie in the blender, and then so this is generated. Okay, this is you're probably familiar with image generation like Midjourney and this type of things. So Midjourney will generate you say pineapple on a chopping board, it will generate beautiful pineapple, but it will be a different kitchen, different pineapple, and so on. So here, what happens? That's what you want. You want to generate same scene, keep the scene, but really just change the state of the scene. Right? And the model is general, so it's supposed to be general. It is general in this example, so it really, actually it is learned on some data, maybe the training it hasn't seen even avocado. Okay, maybe it has seen avocado, but different one for sure. So now we can generate all these steps for avocado. Yeah.
Is it also possible with this that you give the keyboard, like grasp or something, and then it produces for you the image?
I mean, we do.
Or the subcode,
Yeah, we do.
Not that it automatically just use.
I mean, so here we show the states, but we also generate actions.
Yeah.
So I assume that.
No, but if I say this action, can it find for me the keyframe for that? So I want to say, the action of, I don't know, peeling this part of the.
Okay. Yeah. Oh, even sub-actions.
Yeah, okay, yeah, sub-actions.
Okay, you want to do something
exactly
here in the middle.
Because for robotics, this could be very useful.
Right. Okay, so this is really going to like Sora video generation, and you want really which granularity do you want? You want seconds. So
it depends. So some of the actional states are very important.
I think so. One needs to try it's experimental, but I think once it does localize this, because it's all about training data. So now what I described before, it did localize the state 1, state 2 in action, and that's what we trained for generation. But then Yeah, if we can find some consistent intermediate steps between this, then I suppose yes. But it should be tried.
But what I'm saying is that if you have a predefined set of vocabulary, right, like logic predicate for your actions, can you do something with that? That it can, you know, ground implicitly the language with the picture.
Right. So language here.
Yeah.
Okay. Originally, it comes from instructional. Instructional videos. Usually, people don't describe now I'm moving my hand 5 centimeters left. So people describe something more coarse. Yeah. However, I think actually in this work, finally, we did not use this speech transcript. So the image to text models, they are so good nowadays that it's actually almost better to use them instead of what people are talking in these videos. And I think maybe that could be a solution for you, that because there when you like even maybe low level actions like grasping and lifting, maybe you could visual language models maybe could get it, and then yes, you can
basically give text and generate the image.
So you annotate, you run the visual language model like on every frame or maybe every 5th frame, and then yes, and then yeah, that's could be So how do we generate? So again, so first, what do we want? I already described. So here are three methods. Again, how to is ours, and so it keeps the cake, and the other 2 methods, so instruct to pix, and the middle one, so they generate cakes, good or less good, and but the scene is different. That's why our method has something interesting in it. And now, so what? Yeah, I think basically I've talked about this already. So we are using. So if you ask, does it have a notion of the physical scene behind? So it seems like the scene is the same. How does it generate this same scene? There is no physical model, because we don't know how to do it, but it is learned, right? So it's learned from instructional videos. So what I described before. So we decompose instructional videos into state 1, action, state 2, and of course by instructional videos, they are by default they are done in the same scene, right? So people are not just jumping from one scene to another. So by construction, so your training data has the same scene, and that's what the generation network is learning. So it learns to basically preserve the scene. How it does it? So you may have heard of. It seems you know this stable diffusion. Maybe you've heard of, and this is control net. So how many of you have heard of control net? Yeah, some of you. So that's. Control net, that's I think best paper award last year, CPR. It's quite can say simple extension of stable diffusion, but it enables so stable diffusion. It's an image generation network which takes lots of power, needs lots of data, lots of computing power to train from scratch. So what this method is, what it's doing, it enables to take the existing network, image generation network, and fine-tune it a little bit with a condition. And condition could be many different things. And in our case, condition is the text and initial image. So you have a general, okay, so typical network, image generation network would take the text, okay, does some magic, and produce the image which corresponds to this text. So this network is also conditioned on the image, which is initial state, and it will produce something in the same scene, which is described by the text. So the diffusion models, how they work, they estimate the noise. So it's a recursive process where at each recursion it estimates the noise and then it removes the noise from the image. So it's kind of denoising process. And so how much we put the noise into the system. In our case, it's a useful parameters which actually controls our generation. And so if you put little noise, so the image, this is the input image, the first one. And so if we just almost do no denoising, then our output almost doesn't change. The task here is to clean the pan, right? And if you put too much noise, then it completely forgets. And basically, you randomize completely the input image, doesn't know anything of the initial scene anymore. Then you produce just random image of a clean pan. Somewhere in the middle is a sweet spot where hopefully we get something what we want. Right. So the models, these image generation models, they're in general very hard to evaluate. People come up with the papers and just show, okay, this is my image, this is the image of my competitor. My image looks much better. So for the case of for our task, so we know more what we want. Not just beautiful image. We want an image of a particular state or a particular action, and actually we come up with a quantitative evaluation. How is it done? So so say we have a unpeeled apple, for example, and we want now produce an image of a peeled apple. So what we can do, we can first we can collect a data set of peeled apples, okay, with some effort, not much effort, but okay. And now we train a classifier on generated images of peeled apples, and then test it on a data set of real peeled apples. And the intuition is that if your image generator works well, then the model which you train on these images, it will be a good image generator. Sorry, it will produce a good classifier of peeled apples. And okay, that's what what these numbers are about. So the first column is for actions, second column for states, second state, and I think this is the real bound. If you learn it on real images, and then if you learn classify on real images of peeled apples, and then you test it on the test images, you don't get 100 because the classifier is not perfect. You get 96, and we are getting close. Right, so that's this part, and also there's some human study which tells that okay, which image is more actually not just beautiful. It's about the better represents the final state. That's what people think. And also, if it preserves the scene, it does preserve the scene. And some qualitative examples here. But, yes. Okay, any questions to this part? Yeah.
When you say accuracy on the state, it's next state.
Yeah, next state prediction. Yeah.
And next state, how do you define it?
Well, we know. Well, we define it by language. Yes, you tell. Okay, this is my whatever. Give me a. So give me a peeled apple. Okay, so that's.
So basically, it's one time step thing, right? Between the beyond state, one action, one next state. That's it. The whole process is like that.
Yeah, so it's for one step. Yeah,
it's not a continuous time.
No, it's not continuous time. So it's not a video generator. Yeah. So, but probably one could like these are two. Yeah, this is just blending two images. This is not a video. So, but you could imagine now having some model which now video generation model which tries to bridge the 2 frames. Right, so I'll be looking at this time scale axis for a bit, and so first thing, so what we have been looking at is state changes. So these are not huge state changes; these are like I would say order of minutes. So we looked at identifying them automatically in the video and generating them. So what's if we look at the on the left of this time axis, so compared to the right now, so right would be more like task planning. So there's also a problem of motion planning. So that's maybe what, like, how do you bridge this now states? And so one thing one quickly notices is that these instructional videos, they don't talk about people don't talk about like low-level motion. So that's not existent. But still you can have demonstrations, and so I'm going to talk briefly about one work we recently did with a student, which is hand manipulation. So, and okay, actions are here much simpler now. There's no bidding, no. So the action is like grasping something, moving to a particular place, or maybe putting one thing into another. Yeah, I really hope we will get to more interesting action soon, but that's where we are for the moment. And okay, so we don't have textual description of these actions, this low-level motion planning, but we do have demonstrations. And what one can do is to try to estimate the state of the hand of the object, right, and then kind of put it into a simulator and try to learn some policies based on these demonstrations. So now, if you do reconstruct, even if you do very well reconstruction, so you know what will happen. So it won't work because these reconstructions, they are not physically plausible. So they may look good, but actually, and once you put it in a physics simulator and switch on the gravity, then it will fail. So that's not surprising. So what we did and is to I think it's in the realm of other works which are kind of doing similar things. So you try, basically you have a demonstration which is not perfect, and you try to improve it by some exploration typically done with reinforcement learning. So the previous work, actually they tried to do RL, but they did it more in a image space. So because you want eventually you want the task to be solved with the image sensory data. Right? So you don't want to assume you have access to the full system, right? So, but this is hard. So it's actually simpler in this case. Is to once we're already in a state space, we have trajectories in a state space which are close to be good, but they are not good. So we run RL with these demonstration trajectories to improve trajectories in a state space until they are becoming good. And once you have this policy in a state space, it's also good because you can just roll it out for different configurations of your state space, and this will generate much more training data. So basically from one real trajectory, you can generate lots of trajectories in a state space. And once you do this, then you can go back to the image space, or in this case, it's a point cloud. Okay, so you roll out your state-based policy, you generate point clouds, and now you learn visual policy, which takes point cloud and so what we see here, it's still demonstration, but it works well. We don't have the real 5-finger end, unfortunately. But the measurements are now really camera measurements, virtual camera measurements, which senses the point cloud.
Sorry?
Yeah.
What backend are you using for the point clouds?
Which network?
Yeah.
Yeah. So this is PointNet.
Okay.
Or PointNet plus. Yeah. Quite simple. Yeah.
How many demonstrations do you have?
So just one. Yeah.
Just one.
Yeah. So that's also different from other work. So they somehow needed hundreds of demonstrations. So this is just one demonstration. But I mean, originally done here, you generate lots of demonstrations here.
But self-supervised.
Yeah, I mean, you don't need someone. You see the human demonstration, there's one.
What is like trajectory guided reinforcement learning? Is it like you do exploration and that's like what is trajectory guided?
Yeah, I think it's okay. Don't exactly know now to tell, but I think it will be dense rewards so that you are not going far away from the like deep mimic what we discussed today. So you have a trajectory and you try not to go too far from the demonstration trajectory. You allow some exploration, which will eventually help you to succeed on the task, but you don't.
So you basically a reward on basically with a small
deviation from the yes. So in this sense, these policies which I learned, they are not very far from. They're not very diverse. So, but we do diversify them by putting objects in different places and. Okay, so that's few demonstrations, and that's what the hand is doing. Very simple actions. Yeah, some a bit more complex objects. Videos don't play very well. And,
so is it trained on all the objects?
Yes, it's currently trained on each object, yeah. But with just one demonstration. So obviously, the next step, I think that's what students doing now, is trying to generalize it, train it maybe for some objects and then generalize to new objects. So these are a bit more sophisticated actions too, quite simple. So related to the question, what network do we actually use to encode the point clouds? So just a few slides, few slides on a bit better way to do it. So it was a CVR paper last week also. So in image understanding world, so there's pre-training is now known to be very useful. So here is a equivalent, but pre-training for the point cloud. So the idea is to pre-train the point cloud representation for some tasks, which are not necessarily robotics tasks, and then hope that these representations will be also better for robotics tasks. So that's what this paper is about. So sugar, semantic topics and geometry. So okay, so it does. So you have always point cloud, maybe colored point cloud. Colored means that you have RGB on each point, and you solve different tasks such as semantic classification, maybe multi-object scenes. Maybe you want geometry would be segmenting different parts of these scenes, and affordance is how you grasp. So basically, these are all the data sets which we use to pre-train the network. So here is the one collected lots of plausible grasps for different objects. So this would be some classification, 3D segmentation, and so on. Right, and the network here in this case, it's not PointNet, it's a transformer. So you give it as a point cloud as input, also text, because if you text prompts, and then you train it basically for different tasks. So it's quite experimental papers. Most of the papers in computer vision nowadays. So what? Maybe just a few words about results. So these are results for not the target tasks, but for intermediate tasks where we do object classification, segmentation, zero shot first table, zero shot object classification, referring expression grounding, that means you are segmenting parts of the point cloud. And then, so basically we take this pre-trained network and now stick into the policy, robotics policy, which is our playground is RL bench. Some of you are familiar, so they have about, they declared 100 tasks, not all of them are working, but some tasks are working, and so these are the tasks. So it's in a simulation, and so what happens here, so you see that like if you don't do any, like you should look at these numbers here. It's called, so if you don't do any pre-training, it's 87, do the pre-training, it's 293, and so for example, this without grasps, so 91.9, 93.3, so this is contribution of pre-training also on the grasping, so it gives quite 2%, but less 1.5%. Okay, so general conclusion, it does help. Does not help immensely, but it does help to. Why? Probably because in robotics we don't have too much training data. And okay, so this plot may be even more interesting. Is that now in RL bench you usually train from 100 demonstrations for each task. So in reality, you may want to go less demonstrations. So you can go to 10 demonstrations. Then you see that the right. So the pre-training is like if you compare 10 demonstrations without pre-training and 10 demonstrations with pre-training, so there's a huge boost. And in this case, we do test it also on real robots. How we do it? We take pre-trained policy, so it's all point cloud and maybe colored point cloud. So point clouds are reasonably, one can transfer it reasonably well to the real world. Yet, so this is not direct sim to real transfer. So what we do, we take the pre-trained policy and then fine-tune it on a few real examples. So we have demonstrations on a real robot, which we then use for training, and that helps quite a lot. And again, pre-training obviously is important because if you just train it on a few demonstrations, this works very poorly.
How do you do demonstration of the real robot?
How we collect them?
How,
it's not by hand, it's more like script, yeah. So we are scripting. We're putting objects in particular places. And that's
I have a question. Since I have seen in the slide, the data of the pre-training are all on the synthetic data. But as far as I know, there is a very central gap between the point cloud quality of the real world and the synthetic point. So I am concerned about the central gap.
Yeah, that's why you need a bit of. I mean, it's correct. Yeah, there is a gap, and that's why you probably need some real demonstrations. With the synthetic point cloud, it's very clean. I mean, you can put noise, of course, in it, randomized.
I think the noise pattern that's in the real world compounds cannot be simulated.
Yeah, when we tried this, and I mean, like directly transferring, we tried a few things, and directly transferring from simulated trained policies, this point cloud policies, to real world doesn't work. Even if we have exactly the same, we try to make this digital twin of our robotic environment, right? So it's yeah, I mean, probably because of the reasons you say. So the it's not real data and simulated data is not the same. But it's still very helpful to have a pre-trained model even on this non-perfect synthetic data rather than not pre-training.
What exactly is your output here? Because it seems that in between the robots just moving with motion planner.
Right, correct.
So you're
So
just
that's,
doing key points,
yeah,
or?
yeah, that's how the error bench is set up. Is so you the yeah, so the so this is it's in error bench, so they provide supervision. So it's a trajectory supervision, but trajectory is defined by key points. In between key points, it's motion planning. So actually, for all of these tasks, on average, you have 6 key points per task. So it's basically what policy is predicting. It's predicting on average 6 points, X, Y, Z. It's plus if, yeah, if you need to close the grip or open the grip. All right, so I have a few minutes left. So what I want to talk now. So we've been looking a bit on the left part. So I'm also interested in the right part of this time axis, and actually well, we can go quite far on this direction. Okay, it's all planning problems. Like you plan your vacations or you plan your life eventually. So in some sense, these are all planning problems. Maybe not for robotics in the near future, but it's still interesting to see it as one problem. And in this sense, so there are text, you can say, text instructions, books, like how for all these different scales. Maybe not at the lowest, like shortest scale, like on the second milliseconds, we don't have like textual description, but we have books, we have IKEA furniture, and eventually how you live your lives. Probably that's why books are interesting. They learn us something, and so that's on the level of text. And LLMs, of course, they are taking advantage of this. That's why they can pretend to tell you any good advice on anything. So we are now also on the image and video, so we can see the parallel. So there is we looked at the instructional videos, which are more on the level of manuals, and more on the level of books. We have movies. Okay? This is also interesting content to look at, and people did look at it. And so why I'm talking about this, because we just recently, 1 week ago, we released the new data set of movies, or of tasks, movies and the tasks associated with it. And that's what I'm going to talk very briefly about. So first, first, what is in this data set? So these are short, it's called short film data set. These are short films, on average 30 minutes, but they are full stories. They're short, but full stories. So it's like compressed long movies. And lots of different genres. So there are currently about 1,000, more than 1,000 movies in this data set. And in total, about 5,000 questions and answers. So what it means, if you have a movie and you have a question which computer needs to answer. Okay. So it can be open-ended, the computer just answers anything, or multiple choice, where the computer has to choose one of the 5 answers.
the question?
Yeah.
Does it base purely on images or does the audio?
Yeah, audio is included. I'll talk about this in a second. So difference to previous data sets. Well, I'll tell more, but we are not the first movie data set, but first, why movie data set? Because it's not that these instructional videos and egocentric videos, they have their value, but it's different. So here it's more about the story, about people, multiple actors, about their relations, how the relations change and so on. Right, so that's one thing, and then then why yet another? So there are video question answering data sets. Why do we need another one? So we want story level, and story level is not about instructional videos. So movies is a good source of story level video data. They've been story level data sets, but they're commercial movies. If you have commercial movies, then you don't have access to them, or it's very hard. It's not something what you download from internet. And nowadays, if you cannot download from internet, this data is basically is very hard. Nobody can use it. So that's one positive thing with this data set. So it's public. I don't know actually if it's Creative Commons license. I need to check, but it's on YouTube. It's the same level as instructional videos. Right, so you can actually access the pixels of all this. So that's one good thing. So another also important thing is that these movies are, well, actually they are, well, sometimes they're amateur movies, but they are quality. There's a channel, YouTube channel called Omoletto. That's where we get most of them, and it has like thousands of movies. So it is curated. So it's a quality there. However, these movies are, it seems then, just not known to GPT and to other large language models. Why? Because like if you have Titanic, so there are how many articles there are about Titanic on the internet. So what are these numbers and curves? On x-axis, you have the strength of language model. GPT-4 is the biggest one, the strongest one. And on the y-axis, it's accuracy of question answering. So what this shows, so all these models, which are pure language models, they don't look at the images. What they give them, we give them the title of the movie and then the question, and ask them to answer the question. And what we see that the strength of the model for commercial movies, basically they know the answer. They don't need to watch the movie; they already know it. But for our data set, they don't know it because it's.
But how do they know it? It's based on the critics on the internet, or
probably. I mean, there are lots of discussion forums. Yeah.
So basically now, computers are doing critics, and then we watch the videos.
Right. Yeah, they watch the movies and we watch the videos.
Yeah, we watch it. That's good.
Okay, so leakage or data contamination, that's what people call it sometimes also. That's and then another important aspect for computer vision, at least, is that computer vision people talk about long-range video understanding. Means that okay, there's a image level question answering. You give an image and you answer questions. So when you go to video, you hope that you should be reasoning about the like long story, but in fact, often you can still answer a question like from one frame. If you ask what color of the shirt somebody wear at the wedding, okay, so you just need to find the frame of the wedding, and then you get the color and you are done. So you don't need. So you still, it's a search problem. You may need to search like 1 hour of video, but then you answer it from one frame. So so this simulation shows, okay, what we do, try to like we have a question and we divide the video, we chop the video into small chunks. This is called shot. So scenes would be larger chunks and movie would be just one big chunk for the movie. And we try to answer questions either on short level, like scene level, or judgment. The numbers show up. They tell that actually movie level, you get better results on movie level, which gives us hope that it's not just a search problem, that you really need to look at the full movie to answer many of our questions. Okay, almost done. So still quite interesting facts. So here, now we are just benchmarking different models. Say comparing to people. So what is this number? People, we don't give people, we just give people the soundtrack or the transcripts of what people say, and that's the only, and language models as well. So we put them in the same situation, and both computers and people answer questions, and so you see that they're not that far from each other. So like just if you are just given the access to speech, so language models, they are almost as good as people getting there, which is by far not the case if you just give only the silent movies. You give silent movie to people, silent movie to computers. Computers are much worse. So this is, we still have something to do in computer vision. And even worse now, this is also interesting that for people, vision still helps. If you watch the movie, not just soundtrack, but you also actually watch it, so you answer questions by 20% better. For computer vision models, you actually get worse for some reason. Why is that? Yeah, I think the vision is just, I mean, the chance, this is multiple choice, so the chance is 25%. I think all these models, they actually are very bad, almost chance. Why it gets worse, I don't know, maybe, I imagine one can come up with a combination where at least it should be the same, it should be trivial, just killing the image models, but you don't get improvement. That's worrying. Or you can see it as a positive. We still have job to do. Right. So that's I'm done with the movies. So the dataset is online if you are into this. And okay, so that's all for me. So that's summary. I talked about. I think there is still things to do in embodied image and video understanding. So language models don't solve it all, and there are interesting problems on different levels of temporal granularity.
So this is the German way of
Yeah, I used to.
Okay, great. Any questions? So I'll check Zoom. If you have any question, yeah, here you can do it.
Yeah.
You said that one advantage of the short film dataset is that it's not within the training data part models. Isn't that like a constant fight? Because as soon as you put this out there as a dataset, people will take it and train the next generation of models on it. Is there some sort of agreement in the community to just not use certain datasets for these sort of tasks? Or is
I mean, you cannot control what OpenAI is doing.
Yeah, of course.
And the strongest model, they come from industry anyway, so probably they will be used. So I don't think we can really control what they're doing. But well, I think still they will be they are learning from large data. This is okay. It's on internet, but it's very small, and nobody is talking about these movies. So I think it won't be an issue.
Okay.
Yeah. Eventually, maybe it will, but
The more successful it gets, the worse it is.
yeah. I mean, people say like basically you're overfitting to your training data. That's what data collection is. But then there is once your model overfits to the world, then you are done.
Yeah.
Maybe not a question, but a thought. So for these three examples on the top right here, for example, I don't know, the bicycle. So it seems like the model is always kind of predicting the mean of the pictures that's seen. So it assumes a normal bike because maybe it hasn't seen a bike without steering. I would just be interested if there are any approaches on how to like handle these edge cases or pay more attention to the edge cases.
I think if you, I didn't try, but I was happy to find an example which doesn't work. So I stopped there. But I think if you now try to do dialogue and say, for example, next phrase would be, look at the front wheel, is there something wrong with it? So it may actually get it, and then you will ask, well, do you think it can still drive? Then probably it will come to the. So with some iterations of reasoning, and the chain of thought and this type of papers, so they are now known. Like if you provoke the language model to have several explicit iterations of reasoning, it seems to get better. These things could be solved, and it's in some sense it's depressing because it's very out of job at the same. But on the other hand, languages should use it. So if there is such a knowledge already inside there, just find next problem and go further.
Professor, I have an open question. I have researched in the area of embodied AI for about 1 year, and I find in this area the matrix is not perfect.
Benchmark?
Yeah, there are not some well-established benchmark for a task. And for example, for the robot rescue, they have matrix like for closure, like real-world experiment, and like successful rates in a simulation environment. But this matrix, they have both advantage and disadvantage. And since robotics is a system. For example, the successful rates in the real-world experiment is mainly affected by the hand-eye calibration. I find that so in some way the matrix and the benchmark is not so perfect now. So do you have any suggestions for some researchers in embodied AI to find their direction under this imperfect benchmark, imperfect evaluation matrix in this setting? Thank you very much.
Right. I wish I had a good answer. Yeah, we know that computer vision, I think, evolved partly because of lots of data, but partly also because of evaluation. Right, so we know that like progress is often not big steps; it's like small steps, and small steps you need to measure. Yeah, robotics, embodied AI, that's a problem. It's hard to measure because the benchmarks are like real-world benchmarks. Yeah, I think Majid can answer this much better. So I'm pretending to be roboticist. Yeah, I don't have a good answer, unfortunately. I still believe that one could build good simulators of the world. That would be my dream, so that you don't need to test on the real world. And then if you have a great simulator, then I guess you can do benchmarks.
And go and live there.
You can go and live there, yeah. Yeah, so, but, okay, I really wish that people will work more on these simulators. I don't know what it is, not necessarily like explicit physics simulator, maybe something more implicit. But something which you can test and that you know it will work in the real world. But yeah, we don't know how to create that.
It seems a little bit that computer vision is facing a similar problem now, because it used to be very simple. We had data sets or classes like labels, and examples of those labels, and then you could have like a classification accuracy or something like that. But now, as the tasks are getting more diverse or harder or like less concrete, it's also more difficult to to benchmark computer vision stuff. Is that true? Like, for example, if you describe an image with a sentence,
Yeah.
then there's no longer one clear
Right,
metric that
that's
says,
the generative models. They are hard to play.
yeah, so it is sort of a problem that's coming up.
I mean, yes, so that's we inherited from language. Yes, so language is very hard to relate. Yet, actually, I think here, but we are still like, what is the benchmark? But I think evaluation, if we move all the way to robotics and solving tasks, evaluation is actually very objective because either you succeed or not. It doesn't matter, is your intermediate image you generate, is it beautiful or not? It doesn't matter. If you succeed the task, it's good. So then you have just accuracy. So that's what, yeah, we don't have good benchmarks and I don't know how to do it, but I think the objective evaluation, yes, language is hard, like generating images is hard, but if we plug it in into a pipeline which solve the final task, driving or cooking or cleaning the room, then finally, yes, we can evaluate.
More question? I have one question. So do we have any adaptive way to tune the noising, denoising in diffusion model? Like based on the training rate or something like this? How well it's trained, or no, it's just a fixed.
I mean, for us, it was fixed parameter.
Yeah, but do people work on this or no? They say it's good enough. You don't need to.
Yeah, it's again good enough for what? Yes.
Yeah.
Sometimes, yeah, if it's purely aesthetic, so sometimes you want more diversity, sometimes less diversity. So it's.
But if you increase so much the noise, as you said, it's noise. You do not learn anything.
Well, if you put more, I mean, in our system, yeah, if you put more noise, you forget the initial state.
Yeah. And I have one other question. What sugar stands for? I didn't find any G in your.
Oh, it was not G?
I didn't find, maybe. I couldn't detect the acronym.
Geometry.
Geometry. Okay. Returning. Oh, but it's not in the title. Yeah. Okay. Good. Thank you very much. And
Thank you.